Hello everyone, in our last lecture, we were talking about the difference between the solid state drives, SSDs, or the traditional hard drives. So in this lecture and the next one, we're gonna complete the Windows forensics, and we will talk about the different file systems that are there for Windows, how those file systems work, and what are their unique features. So before jumping into that, there are two interesting topics that we need to cover. The first one is the understanding the boot sequence. So if you guys remember in chapter one, or say in the very first or second lecture, I mentioned that, whenever you are doing forensic investigation, even if you don't do anything on the computer, just powering the computer on or just turning on the computer will have some, read and write operations done on the hard drive, and it can change some content of the hard drive. So now we'll be looking into or seeing how the boot sequence works. Like for example, when you turn on or power on a PC, what are the different write and read operations that are done on the hard drive, and how the overall computer starts, and which regions of the hard drive are accessed in order to get the data from them. So, first of all, one of the most important things in any computer is its BIOS or its EFI. So, what is a BIOS or a EFI? BIOS is a firmware of your motherboard. So, all of the motherboards, like every computer, will have a motherboard which will have different components, and on that motherboard, it will also have BIOS or EFI. So both of these things, BIOS and EFI, these are, you can call in simple terms, the firmware for your motherboard, and this contains the basic information that is required in order to start the whole physical machinery, like your CPU, your memory, and other components of the hard drive on your motherboard, as well as loading the operating system. So there are two versions of the this motherboard firmware. First one is BIOS, and the other one is EFI. Now it also like has another thing which is UEFI, which is an upgrade on these two systems. Another interesting thing on your motherboard that you would find is CMOS. So what is a CMOS? CMOS is basically a random access memory. So it's a volatile memory which contains the information about the system configuration. It also contains the information about the boot sequence, like how the booting process will start. And it also contains the information about the time and date, whenever you power your PC on. So because of this CMOS, and since it contains the information about date and time, current date and time, no matter if you turn on your PC, say after a week or 2 weeks or 3 weeks, it will show you the accurate time, or it will show you the current time. So your PCs or your computers, they take care, or they keep a track of time using the CMOS mechanism, or using the CMOS volatile memory. So this CMOS, since it's a volatile memory, so all volatile memories, they will be wiped out in case they lose power. So in order to provide power to CMOS, if you guys open your computer, like maybe not the laptops, but the other computers, you will see that there is actually like a power cell, a small battery that is placed on the motherboard just to power the CMOS. And if you take that battery out, your PC will it will lose the information about the current time, as well as some other critical information that is required to boot the whole PC. So these are the different steps that your PC or laptop or any computer takes when it is powering on. So the first thing is, like when you press the power button on your PC or on your laptop, the first thing that the computer will do is to load the firmware in the BIOS, EFI, or UFI, wherever, like whatever it is on your motherboard, depending on the versions and all. So the first thing will be to, powering on the whole machine and reading the firmware. So the first thing after reading the firmware, what the firmware will do is it will do a post test. So post is power on self test. So your firmware, BIOS or UFI or EFI, it will test different components, like different physical components on your PC or on your motherboard, such as your RAM, your ROM, your if there is like any GPU, if there is any CPU, all of those things, BIOS will run them, and will send some commands, get some like response back from these devices, and based on that, it will figure out if all the physical devices, such as, like RAM, ROM, hard drive, everything, it is working on. That's why you see, like, if you unplug, or say, like, if there was a GPU, or if you like pull out the CPU, or pull out the hard drive, there is no hard drive in your computer, then in the power on test or post test, it will fail that. And when you are turning on your PC, you will see an error that there is no hard drive, or there is no storage located, or no storage found. So that is done by the post test. So after performing the post test, when BIOS finds out, or the firmware finds out that everything is working fine, the next thing is to figure out where to boot the program. So for that, the firmware or BIOS will communicate with the CMOS. It will ask CMOS for the information that where is the bootable sector, or where is the starting point of the operating system, or say a program that will like load the operating system. So it will get that information from CMOS. Then for example, CMOS will tell BIOS that there is a hard drive, say, hard drive 1 connected on this PC, and that hard drive contains the bootable software or the bootloader. Then BIOS will communicate with that hard drive's firmware, and it will tell or ask that hard drive to give it the bootloader. So what is a bootloader? So bootloader is basically a small program that is generally written on the first sector of the hard drive, and that contains the information of the operating system, like where in the hard drive is operating system installed. So the firmware or BIOS will get the information, or get this bootloader from your hard drive, and then it will run that program. So bootloader is a very small program, and its only job is to actually find the operating system, like where the operating system starts in the hard drive. So it will find the operating system, and then the operating system will be loaded into like your PC, and then your whole PC will start working, or will start running different components of the operating system. Like it will start the kernel, and then like the whole user interface and everything else. So this is how the whole system works when you power on your PC. And as you can see, like before the user can type in anything, there are so many different reads and write operations. For example, like BIOS starts, then it reads information from CMOS. CMOS gives it the information about the hard drive. Then, it reads the boot sector or the bootloader from the hard drive, and then opens or starts the operating system. So all these read and write operations, they are done before the user can even press one key, or before the user can even, like do anything from the user space. So when we are like getting the information, or whenever we are doing forensic analysis, we want to like minimize these things as well. So if we have physical access to the PC, that's why it is very much like preferred to pull out the hard drive and use a write blocker. So all of these things, they don't happen, and you just read the data from the hard drive, or copy it bit by bit. Now, given all this information, like we know, or we now understand how the boot sequence works, or what steps happen in the background when a PC starts, let's talk about file systems. So what is a file system? A file system is basically a software which manages how data will be read from the hard drive, or how data will be written on the hard drive. So your operating system doesn't have a direct communication with your hard drive. It is the file system that acts as, like the middleman between the two. The operating system, whenever it wants to write some file or read some data from the file, it will tell the file system. The file system will basically find that data in the hard drive, and it will show it to the operating system. Similarly, when the operating system wants to store some file on the hard drive, or store some data on the hard drive, it will give that data to the file system, and the file system will find the actual sectors on the hard drive that are available, and it will store the data over there. So first thing, it acts as a middleman between the operating system as well as and the hard drive. The second thing is the file system keeps track of all the files and folders that are there on your PC. So for example, starting from the operating system files to user files, what are those files, what are the directories, for example, the folders, what are their names, what are the file names, the metadata when the file was created, and so on, as well as the actual data as well. So all of these things, all of these different attributes of a file, its name, permissions, its data or its content, all that is stored in the file system. So from like digital forensics perspective, even though both of these things they look similar, operating system and file system, but these are two different things. Operating system is the user interface, or the like it provides us the GUI or a nice interface to interact with the hardware. File system, on the other hand, keeps track of and manages, or keeps track of all the files and manages like the communication between the OS and the hard drive. So there can be like multiple different there are different types of file systems. We will study two main types for Windows. The first one is NTFS, and the second one is FAT. So we'll learn them one by one. And then in FAT, you have like so many different versions of FAT that you might see in your like forensic analysis. When you are doing forensic analysis, depending on the device, you will see different operating system and as well as different file systems. So now the one operating system can support multiple file systems. For example, you can have two drives, one running NTFS file system and the other running the FAT file system. Similarly, like one PC can have multiple operating systems as well. So you may have, like Windows as well as Linux installed on your PC, and maybe the both of these operating systems, the underlying file system on your hard drive is the same. For example, FAT for both of them or NTFS for both of them, as well as if you have multiple partitions, they can have different file systems as well. So it is very important to understand the difference, that even though they look familiar, sound familiar, similar operating system and file system, but these are two different things. So before we jump into, like the file systems for Windows, we need to see the file structure or how the hard drive structure looks like. So we discussed this in the beginning. Just want to reiterate that the operating system sees a hard drive as a combination of clusters, and it will have, like cluster numbers. It will assign cluster numbers 1, 2, 3, 4, 5, 6, and so on. So the operating system, when it wants to, like, or when it looks at the hard drive, it just sees hard drive as a group of clusters. But we know that the hard drive is not a group of clusters. In fact, it has different sectors, and one sector or one cluster can have one or two or three, like more than one sectors combined together. So when you like write the file system or like format a hard drive with any particular file system, this information, like how many sectors are there in one cluster, you can manipulate or you can change that when you are like booting or when you are formatting the hard drive with any particular file system. So cluster is the storage allocation unit that is seen by, or the allocation data allocation unit that is seen by the operating system, whereas sector is the actual or the smallest data unit in which you can read or write data on the hard drive. And file system is the middleman which converts the cluster numbers, which are logical numbers or logical addresses, into the actual sector numbers, which are the physical addresses. So the OS, it assigns different logical numbers or logical addresses like cluster number 1, cluster 2, cluster 3, cluster 4. As you can see here, the screen like set of 3 sectors is one cluster. So the operating system will see the hard drive as set of clusters. It will assign different cluster numbers. The file system will convert those actual cluster numbers into the physical addresses. So it will communicate with the hard drive, and it will know that cluster number 1 is maybe one sector from here, here, and here. So sector number 1, 2, 3 is cluster number 1. Similarly, cluster number 2, maybe it is sector number say 20, 21, 22. So they don't have to be close to each other. They can be located on different spaces or different locations within a hard drive. So given this information in mind, the next thing we need to talk about is the disk partition. So what is a disk partition is basically you can divide one physical hard drive into multiple logical drives. So you can say, for example, if one hard drive contains 2000 different sectors, you can divide those 2000 sectors in two different logical drives, and each of the logical drive will have 1000 sectors each. So in this way, you can create one or more regions on the hard drive, and these regions, they are called disk partitions. So every partition, or every hard drive that you have, it will have a partition table. So what is partition table? The first sector of the hard drive, it will contain master root record, master boot record, sorry, or MBR. So MBR has like one sector is 512 bytes. The first 444 bytes, they are for the boot sector or the bootloader that we just discussed earlier. The last 64 bytes are your partition table. And this partition table contains the information like how many disk partition, like logical partitions are there on this particular hard drive, which sectors belong to, and also like which sectors belong to which partition. So for example, in our case, or in the example that we discussed, you have like one hard drive which has 2000 sectors. So this MBR table, partition table in the MBR will say that, partition one, sector number 0 to 999. So it is basically telling that these sectors, they belong to this logical partition. It will have another entry, which will be, partition number 2 or logical partition number 2, and it contains sector number 1000, and it goes till 1999. So this way, your partition table has the information about which sectors belong to which particular logical drive, and where from which sector that logical drives begin and end, like the boundaries and total number of sectors allocated to each of these partitions. Another interesting thing is the partition gap. So sometimes, like you can, for example, this is, I think, all of you struggled on this in your lab one when we were creating disk partitions. So if you shrink a partition or if you delete a partition, there will be some unused space between the two logical partitions on your hard drive. So that unused space is called partition gap, and you can actually, create a partition in the allocation gap or unallocated space, store some data there, and then delete that partition. So if you, delete the partition name, for example, A, B, C, D, E, F, G, H, whatever drive name or number you gave it, if you delete that, then your operating system will not show you that partition when you open my computer. So this way you can, have hidden partitions as well that are not assigned any particular letter. So if a partition is not assigned a letter, then it will not be visible in the operating system, and you will have some hidden data, or you can, store hidden files and everything in those hidden partitions. So things to remember: what is a disk partition? You are basically dividing one physical hard drive into multiple logical partitions. Where this information will be stored, it will be stored in the first sector. First sector of a disk is basically MBR, master boot record. It contains the bootloader. First 444 bytes are bootloader, 446, and the remaining 64 bytes, they are partition table. So there are different versions, like for example, the virtual machines that you used in your lab, they have the master boot record, like this is the mechanism in the hardware. In some cases you will have GPT. So one drawback of master boot record is that you can have maximum of 4 partitions. That's why you guys were getting errors whenever you were trying to create more than 4 partitions. It was telling you that you cannot create more than 4 partitions, right? So a logical partition is just a division, or say subset of a physical, actual physical hard drive, and the information that which sectors belong to which partition and from which sector the partition starts, like and ends, the boundaries and total number of sectors, it is stored in the master in the MBR, and where specifically in the MBR and the partition table. Now, the next question is, why do we need partitions? Like, what are the advantages of partitions, and what are the cases or, scenarios where partition doesn't work or is not that much helpful? So the first very basic advantage of partitions is that you can have the partitions to organize your data better. So for example, rather than having one large hard drive, you can create two logical partitions, C and D. In C partition, you can store your operating system, as well as you can store some, like basic programs that you use. And in D partition, you can have your all other user related, files or programs. So if you want to store games, or if you want to, like store movies, pictures, songs, those type of things, you can store them or organize them in the other partition. The other thing is different file systems as well. So you can, have one file system on one logical drive and another file system on the second drive. So for example, in our case, we can have, NTFS on C partition, or say logical drive C, and we can have FAT file system on the D partition. So you can have multiple file systems as well on different or logical partitions. Then another advantage is we can use or we can create a partition just for backup and just store our data, like important data on the backup partition. So even if the main partition or the primary partition or C or D gets corrupted for somehow, maybe because of a virus or something like that, we'll have our data stored in a backup partition. Then there is advantage of speed that for the HDTs or the magnetic drives, the partitions that are like on the outer side of the physical drive, reading and writing data from there is typically easy. Then we have the security. So, NTFS provides us the option for, encrypting the files, or you can also encrypt the whole partition as well. So if you want to encrypt, or if you have, say, some important data that you want encrypted, so rather than encrypting the whole hard drive, say if you have 1 TB hard drive, you will need to encrypt the whole hard drive. Another way or a better way would be you just create a small partition for your important data and just encrypt that small partition. So in this way, it will, take less time in updating those files that are encrypted, as well as, decrypting the files. And also another advantage is multiple booting, or you can have two different operating systems in those logical drives. So maybe you can have Windows on C drive and you can have Linux on D drive. So that is another advantage. So what are some cases where, like partition might not be, that beneficial, or what are the drawbacks of partitions? The first and foremost is drive letters. So for all the physical hard drives that have the MBR or master boot record to store the partition table, you have just four, you can create just four different partitions. So that's why you guys were struggling whenever you wanted to create more than four partition, even if you have unallocated space. The next thing is backup oversight. So if you have, multiple partitions created, and you want to have some backup or some files stored in those backup partitions, then it will be up to you that which of the partitions you want to dedicate for backup and what type of files you want to store there. So speed is it can be like, it can work both ways. It can, for some cases it can speed up the whole reading and writing operation. For some cases it may slow down the performance as well. And lastly is the false security. So again, it is like a counterpart of this portion here, where you have some important documents and you stored them on a partition and you encrypted it. Now only that partition will be encrypted, whereas your whole disk, or the remaining part, it will still be unencrypted. So there can be, sometimes mishaps can happen. So maybe rather than storing your important data on that encrypted drive, you may store it somewhere else, and that will be visible. Alrighty. So different partitions and the different, file systems that you can have, they have different associated codes. So for example, FAT12, the code is 1, FAT16, the code is 4, NTFS and exFAT, they have the code for of 17, FAT32 is 0B, and so on. So the different versions of file systems that we see, they have their own unique codes that can be used to identify those particular file systems and partitions. So first we have the FAT, or which is file allocation table. So what is FAT? FAT is a file system that was developed by Microsoft, and it was originally developed for floppy disks. So that's why you see over the time there has been different versions of FAT. It started from FAT 8, then 12, 16, 32, exFAT, and so on. So what does these different numbers tell us? So these different number that tell us like how many, what is the size of the one entry in the FAT allocation table, and from that we can infer that how many total number of entries are there in the FAT table as well. So you can simply say that FAT8 has 2 to the power 8 entries in the FAT, or it can has 2 to the power 8 clusters in a file, and a system with FAT32, it can support up to 2 to the power 26 clusters. So this is the basic layout of a disk or a volume which has FAT or file allocation table, FAT file system installed. So there are two basic things. The first one is the directory table, or simply, like file directory. And the other one is the file allocation table, or the FAT table. So these both of these things, they have their own purpose, and we will look into them one by one. So before that, just imagine that you are a user and you are using Windows, and you want to store a file called file.txt in the folder foo. So what will happen is, just suppose that this file.txt, it has four different blocks. So maybe, it has 512 bytes of data, then 512 additional 3 and 4. So you have total around 2000 bytes of data that you want to store. So what will happen is the operating system will contact the directory table, and it will tell the directory table that I want to store this file.txt in this folder foo. So what is the directory table? Directory table is a table where each directory or each folder in your operating system or in your computer has one entry. What are the components of this? The entries on the directory table, you will have the file number or file name or directory name. So for example, we want to store a file foo. So it will have this file name or directory name as foo. Then it will have the number of starting block. So what is a starting block? It is basically the sector number or the logical number of the sector where this data will be stored. And then it will have other metadata, like when this file or folder was created, who created it, like different permissions and those type of things. So in order to store the file.txt in the folder foo, first the directory table will create one entry for this folder foo. So wherever, like, this is a hierarchical table, depending on, what is the root folder for foo, it will create one entry for that. File name or folder name will be foo. Starting block one, which tells us where, the information or the components of this folder are stored at. Now, if we just look at this block number or cluster number, we can go to the next entry of this directory table, which will contain the information about this individual file. So again, we will have the file or directory number. So in this case, we have file.txt. Then we have the starting block, like where, or the starting cluster, that from which cluster this file's data starts from. And then some other metadata that will be related to the file, like when it was created, who created it, modified it, and those things. On the other hand, after doing both these operations, on the other hand, we have a file allocation table. So it is just a big table which has different things. First is the number of clusters. So it will have cluster number one, cluster number two, three, four, five, six, seven, and so on. Then it will have another bit that represents whether this cluster is in use by some file or whether it is empty and it is available for writing the data. And then next is, it will have a next pointer, which tells us that, if we are talking about file, read the data in this particular cluster and then go to the next cluster to get the next data. So for example, you can see here file.txt, it has different blocks. So we can store one block in one cluster, and then we will have a next pointer, which tells us the address of the next cluster in this particular file chain. So you can think of this whole thing as a linked list, where you are provided in the directory table the starting point or the head of the linked list, and then you will have to traverse that linked list in order to find any particular file. So here, this foo, which is our directory, its starting block is 1. So we'll go into our FAT table. We will find here the cluster number 1. It is occupied because we just wrote the foo or this particular directory's information in it. And then it tells that next pointer is -1. So the -1 tells us that this is the end of the file. Since this foo is just basically one directory, it doesn't have, so much data in it. So all of the information that is there in one directory, it can be stored in one cluster. So the first cluster is occupied, it is busy, and it doesn't have like any next cluster. So it's just one cluster and it is used to store foo. Then if we read the data of the cluster number 1, we will see this particular entry, which is file.txt. So it is the name of the file, then its starting block and the remaining metadata. So when we want to retrieve the data of this particular file, we will have to go there to the file allocation table again. We will look into cluster number 2. It is busy. We will read the data, whatever data, or like this content right here, give it to the operating system. Then it tells us that the next block in this particular file is on cluster number 6. So we will jump here, go to cluster number 6. Again, it is busy because we just wrote the data in it. Then we will read the data in this cluster. We find the next cluster as 3. We will jump back to 3, read the data. Next, we have pointer or cluster number 5. So we'll go to cluster number 5, read the data from here, and then there is no next pointer or there is no next cluster. So that tells us that this whole file, we have 4 blocks and we have read all those 4 blocks. One thing, sorry, I missed, like if you want to write the data, the operating system, when it tells the file system, it will create these 2 entries and it will give you the starting data or the starting cluster number. So when you are writing this file, you will come on the starting cluster, cluster number 2, you will change this busy bit to 1 and write the first block of data here. Then next block, the file system will give you that use block number 6 or cluster number 6. So we'll go to cluster number 6, change it into 1, store the second half of the data here. Next, we have assigned cluster number 3. We go to cluster number 3 and store this block right here. And next is block number 5 or cluster number 5, where we will store the last block. So in this way, you can store different blocks of data of a file into the file system. And the file system just creates, like a big linked list of different clusters. And for every file, it gives you the starting point or the starting cluster where that linked list starts from. And then you go and look into this FAT or file allocation table. Here you have the cluster numbers, the busy bit. If it is 0, that means the cluster is free. If it is 1, that means the cluster is in use by some file. And the next pointer, which tells you that if this is the last cluster of a file or if there are multiple clusters here. So this is how the reading and writing operation will happen. When you are writing some data, you will have to create first a entry for that particular file in the directory table, get the first starting cluster from the directory table, and then start filling or writing these blocks one by one into the clusters that are provided by the file system. When you want to read a file, just follow the file from this directory table, follow the hierarchy, go to that particular file, gets its starting block or starting cluster number, and then just follow this FAT or file allocation table. Just like you follow a linked list, you go to the head, and then one node, then you have the next node, then the next node, and so on. So it will point you to the next sector, and when the pointer is -1, that tells that there is no next sector in this particular file, and this is the end of the file. So given how this is how files are written and read from any hard drive that has file allocation table, this is how file allocation table works. So 2 important things: FAT, which is the actual file allocation table, a table which has all the clusters. It also gives you the information whether they are busy or not, and the next clusters, and the directory table. This is the basic layout. Like if you have a FAT file system on your hard drive, what information will be stored in which clusters, or sorry, in which sectors. So the first sector of your hard drive, it will be your boot sector. And this sector will contain the MBR. The MBR we just talked about in previous slides, that has your bootloader, which is, a small program that will start your operating system or locate the operating system and start it from there. And the last 64 byte of partition table. So the whole MBR 512 bytes, that is in your boot sector, and that is typically the first sector of your hard drive. After that, you will have another sector, couple of sectors that are reserved for the file system information. And this contains, information such as how many bytes are there in one sector, how many sectors will comprise or, will add together to form one cluster, what is the maximum number of files or clusters that are in the FAT allocation table, and so on. After that, you will have 2 copies of your file allocation table. Like this file allocation table, you will have 2 copies of it. So why do we need 2 copies? It is because for data redundancy, that even if some, like FAT1 or the first copy fails or it has some error, we will have a working copy and we can, get the file details from the second or the mirror copy. Then it has, the root directory or directory table, this table right here. it will be after the file allocation table. So this table contains, the directory table contains all the information like the starting points, mid, and the metadata about different files as well as directories. And then all the remaining sectors, or all the remaining clusters that are there on your hard drive, they will be available for reading and writing data for various files. So here is another example. So you have the FAT file system stored on one particular hard drive. So you have this boot sector, the first sector 0. Then you have, this information, file system information, then two copies of FAT1 and FAT2. Then you will have the root directory. So whenever you want to retrieve a file or write a file, you will first have to go and look into the root directory. In root directory, you will see this information about different files, like what are the name of the file or the folder, and what is the starting block and some metadata. And after that, you can just start following this. So here in this particular example, we have two files. The first one is a JPG file, tyui.jpg, and the second one is a doc file. So if you look at the, after reading the root directory, this is how the root directory will look like. It has the file name, and then the starting cluster, cluster number 2, and then the length, like what is the total size of the file. So if we want to read data from this file tyui.jpg, we will first go look into the cluster number 2, read the data from cluster number 2, then we will go look into our file system, and the next cluster after this is 3. So we'll go to cluster number 3, read the data from there. Then the next cluster is 4. We'll go to cluster number 4, read the data from there. And then we have this 0x and 3f, fff. So this is for, indicating that this is the end of the file. So in this table, I represented it with -1, but actually, like in actual terms, it's 0x fff. And in different, versions of FAT, you will have multiple Fs. So here we have 3. So it's like, 2 bytes, or say 1.5 byte. But in other, like, FAT 16 or FAT 32, you will have like 2 bytes or 3 bytes just representing all Fs. So this all Fs is used to represent the ending of the file. Like this is the last cluster in this particular file. So this file TUI.jpg, it is stored in 3 clusters, basically cluster number 2, cluster number 3, and cluster number 4. And if you just want to read it, just get this entry, get the starting cluster from the root directory, and then just follow the linked list. Similarly, other file, it is mes.doc. Its starting cluster is cluster 5. So all we have to do is just, go to cluster number 5 and follow the different entries in this file allocation table, like we follow a linked list. So go to cluster number 5, read the data, whatever data is there on cluster 5, and then the cluster 5 tells you that the next pointer is cluster number 6. Go to cluster number 6, read the data from there, and it shows you that it is 0x fff. So that means that is the last cluster. So file number, the second file, mes.doc, it consists of 2 clusters, cluster number 5 and cluster number 6. Now the remaining clusters, you can see here, they are unused or unallocated at this time. So if you, want to store the third file, or if you maybe, somehow, if this is a doc file and you add more data into it, it can utilize these empty clusters that are available to you. Now, the next thing is what happens when you delete a file, or how you can delete a file. So whenever the user wants to delete a file, the first thing that, the file system will do is that it will replace the first letter of the file name with a hex letter E5. So if you go into the directory table, this file.txt, if we want to delete it, it will be, like an EX5 will be added, E5 will be added before it. So this file will come E5 file.txt. So that E5 or that 1 byte tells the file system that this entry is deleted. So what it will do is that, the starting block cluster, it will change it, like delete this information as well. Then whatever clusters were utilized in this particular file. So here we had 3 basic clusters. So starting from 2, then we had 6, then we had cluster number 3 and cluster number 5. So all these 4 clusters that were allocated to this particular file, after writing E5 and removing the starting block entry of this particular file system or FAT will also change this busy bits to 0. What will happen when it changes these busy bits to 0? then these clusters become available again. Even though the data of this file.txt is still written on these clusters, we haven't wiped that data out, but they will be they will be made available again for writing operation. And whenever you write some other file, the file system may allocate these same clusters to those files or to the next file, and the next file can overwrite the data. So the first part is that, or the first step is that you change the first letter and you replace it with E5 in the directory table. Then that tells the directory that this file is deleted, it's no more. Then we will set 0 for all the fat chain for the clusters in the fat chain that were allocated to this particular file. So all these bits, they will busy bits, they will be turned into 0. That tells the file system that these clusters are available again. So the data will remain there unless it is overwritten. In hard drives, in SSDs, once you change this available to 1 to 0 again, the garbage collection that we discussed in the last lecture, it will wipe out the entire data. All right. So this is how, if you open or say like, you make a image of a USB drive with a FAT file system or hard drive with a file system, and you open it into Autopsy, you can actually see these different folders. So all the different things like, the boot sector, the file system information, the two FAT entries, root directories, data region, all that, you can see that in the Autopsy when you open a file or when you open an image of a hard drive or a USB drive that has the FAT file system. So here is an example of FAT32. You can see there is the first directory, root directory, which is, like a directory that contains the information about all the files and folders that are there. Unallocated, this is actually the free space, or, which sectors are available there. We have two copies, FAT1, FAT2. Then we have some reserved sectors. So what are reserved sectors? They are reserved for specific purposes and they are not available for the file system to write the data. So this way you can see all of these smaller, or say individual components of a file system in Autopsy whenever you open any image. So there are different versions of FAT, as I mentioned before. So we have FAT 8, FAT 12, 16, 32, exFAT, and so on. So what are these different versions? Basically, they tell us like what is the size of each entry in the FAT file system. So for example, here in this particular thing, some bytes in this one entry in the file allocation table, it will be used for cluster numbers. So if you have more space, then you can have larger cluster numbers. So that's why FAT12, which has just 12 bits for one entry in the FAT allocation table, maximum number of clusters that it can have is 2 to the power 8, which is 4096. FAT16, maximum clusters that you can have is 16 bits. So 2 to the power 16, 65536, and so on. So as the FAT number increases, that means the size of each entry in the FAT table also increase, which eventually means that you can have more numbers, or more you can say number IDs available for different clusters. So you can have multiple clusters in one particular file allocation table. That's why FAT12 was used for floppy disks or very small size hard drives. Then FAT16, this is, you can commonly find it in USB drives. And then the hard drives, they generally have the FAT32 and exFAT. So you can see here they can have like millions of clusters. So you can have large scale hard drives up to 2 TBs or up to 128 PBs. The other thing is, like, as the file number increase, the supported cluster size also increases. So FAT12 has the cluster size, like the standard cluster size of one sector, which is 512 bytes, to 8 sectors or 4 KB. So as the FAT versions increase, the number or the size of individual cluster also increases. So this kind of concludes all the information that you need to know about the FAT file system, how files are stored, what are the different components like of the file system. We have the FAT allocation table as well as the directory or the root directory. Then we have the layout, like what are the different, what are the different components within the file system that are, you have the boot sector, which is the sector 0. Then you have some reserved sectors for file allocation or file system information. Then you have two fat tables, two mirror copies, same copies, just for redundancy, that if any one of them gets corrupted, the other will be available. And then you have, some other data regions where it contains like which sectors are available for writing the data. So you can have that information stored there. The next topic is very interesting, and this topic is called Slack space. So we'll discuss what Slack space is, how we can find Slack space, and what are the implications, or why do we need to know about Slack space in terms of cybersecurity or and digital forensics? Like, what are the informations that we can extract from there? So before we jump into that, you can do this exercise, like open any file. If you guys are using Windows, open any file, right click on it, go to properties. And when you go to properties, you will see that there are two different sizes. One, so in this particular example, this is a text file, tt.doc, and you can see that there are two different size values. One is size and the other one is size on disk. So a question might come in your mind that why there are two different sizes. What does these two different sizes tell us, right? So the first size, which is just size, it tells us that what is the size of the actual content of this particular file. So for example, if you write, say, one line of text or two lines of text in this tt.doc, then the size will tell you that how much is the size, like how many bytes of data the user wrote in this particular file. The next thing is size on disk. So this tells you that how many clusters are allocated to this particular file. So here, like depending on the actual, your configuration, you may have, cluster size of one cluster is equal to 6 or 8 sectors. And as we know that cluster is the smallest unit that the file allocation or the file system will allocate to any particular file. And this is also the smallest unit in which the operating system sees a file. So even if your, content is way less than that, even if it's 1 or 2 bytes, the file system will allocate one complete cluster for that. So that's why you see these two different sizes. The simple size is the total size of the actual data of the user, or say in this case, whatever is the data size for tt.doc, and size on disk is how many clusters were allocated for this particular file, like the total size of the clusters allocated for this particular file. So in this case, we can see that, the actual size is 1.14 kilobytes, or 1172 bytes, and total there were 4096 bytes, or 8 sectors that were allocated to this particular file. So there will be some empty space, and that empty space is basically called slack space. So this is another observation or another example. So, just imagine in this particular example, we have cluster size equal to 4 sectors. So the minimum space or physical space that the file system will allocate to one file is one cluster, and it will be for 4 sectors. Maybe the actual data of that file doesn't fill the 4 sectors completely or one cluster completely. So you will have some empty space left within that particular cluster. It can be one sector, or it can be, like multiple sectors empty. And this space is called drive slack or just slack space. Here is another example. So now in this particular example, we have one cluster equal to 8 sectors. So this is exactly this particular example you can see here, or the same cluster size. So here we have one cluster. So when the file system allocates, some space, it will to any particular file. The minimum space that it can allocate is one cluster. So it will allocate all these 8 sectors to one particular file. Now the actual file data is just 2248 bytes. So it will fill cluster or sector number 1, 2, 3, 4. At 3 and 4 cluster will be filled partially. This is the fifth cluster starting from 0, 1, 2, 3, 4, and the fifth one will be partially filled. Now, how many clusters are there remaining, or what is the empty space that is there? So we have 3 complete sectors that are available in this cluster. So all these sector number 5, 6, and 7, they were completely untouched. So there was no data that was written in this particular region. So this or like space, or the the total space that is not touched by the any file. We call it cluster slack. That tells us that how many sectors are free. So here we have three sectors that are totally untouched by this particular file. So our total cluster slack is 1536 byte. The sector number 4 is interesting. Why? Because it contains half of the data from the file, and the remaining half is RAM slack. Now, what is RAM slack? That is the next question that might come in your mind. So, before we, go in detail, so you guys have to go back into the previous lectures. I mentioned that, all the applications, for example, when you open Microsoft Word, you double click on Microsoft Word, that application is pulled into your RAM, or the, volatile memory of your computer. And that's where whatever you do, you are doing or running the application in RAM. So whenever you open Microsoft Word and you start typing, whatever you are typing, your data, it stays in RAM until you save that file. So the RAM, it has different pages. That's the unit that is used to store the data in RAM, or the smallest unit of data that can be utilized or used in RAM. And generally one page and one sector, they have the same size. Now they are optimizing the sector sizes. They are making the sector size to equal to 4 KB, just to match those two things. But for this particular example, you can think that one sector is equal to one page. So this is how the data will look like in RAM. So you will have, the first page or the first sector completely filled by user data. Second will be completely filled by user data. The third one will be half filled by the user data. But when you transfer, like when you save this file on the hard drive from your RAM, then what will RAM do? It will, fill this empty page or empty sector with some bunch of zeros. So this info, region of the sector, or the empty region in the sector, that is, left within the RAM, left empty inside the RAM. This is your RAM slack, and then the whole thing, this is your file slack or cluster slack. So coming back to this example, three sectors, they were completely untouched, and these are cluster slack. So you can just total them. One sector is 512 bytes, so you can total these three. It gives you 1536. Now the sector number 4, it contain half of the data of the file, and the remaining half as RAM slack. Why? Because when we were copying this sector from RAM, then half of it was user data. The remaining half, RAM itself filled this remaining half with all zeros. Because when we are copying data from RAM to hard drive, storing it, one sector is the smallest unit, or in which we can make that transaction. So we have to, even if the data of the file is half of sector number 4, we will have to read the entire sector number 4 into the hard drive and write it over there. So here, like, what is your total slack space? It is the sum of your RAM slack and the cluster slack, or the file slack. Or you can otherwise say that it is the difference between your actual size, the size of the data, minus it or subtract it from the size on the disk. So if you subtract these two, then you will get the total slack space that is available there. All right. So now the next question is why the slack space is important. Like, what are the forensic implications of the slack space, how it can be used, what we can retrieve from here. So let's look into that. So imagine this is one cluster that is allocated to file number 1. And you can see that this cluster consists of total 8 sectors. So we write the file 1 on this particular cluster. And you can see that this file occupied around 7.5 clusters or 6.5 clusters. The seventh one is half empty, and the last sector is completely empty. So this space right here is the file slack for file number 1. Now imagine that we deleted this file. Somehow, the user doesn't need it anymore, and the user deleted this file. Will this delete this entire data? The answer is no. Why? Because we just discovered, or analyzed when we are talking about FAT file system, that whenever you delete the data stays there only those clusters or those sectors, they are made available again. So if you delete this file one, the file system will just make this cluster available again, but the data will still stay there. Now just imagine that this sector is now allocated to some other file, file number 2, and the file system writes the other file. And this is the amount of content that the file number 2 will write on this particular cluster. Now, as you can see that we have the new content from file number 2, but there is still the remnants of file number 1 still lying on this particular cluster or still lying on this hard drive. So this is the file slack for the file number 2. So if we look, or if we say just, like copy paste this whole cluster, copy this whole cluster byte by byte, we will see that it contains the data from file number 2. And then it also contains the information or data of the deleted files that is still lying in the file slack. So if you just retrieve this portion of, or, like look into this portion of the data, you will see information of the deleted files. So here's another example. So, we just opened one file in any hex editor. You can do it yourself as well. And you can see that this is the end of the file data, or this is the end of the, user data that the user wrote. He just wrote, I am here. And then all these remaining things, they are just basically file slack. So all these bytes that you see here that are untouched, and like sometimes they can contain information if that this particular cluster that is assigned for test.txt, if it has been assigned previously for some other file, then we can see the bytes of that particular file, or the deleted file here. So this way, by examining the slack space, we can extract the data from the deleted files that might have been deleted in the past, and we can still find some important data out of them. So this is like just an exercise for you guys, and it just tells you that how many sectors are there, what is the size of, like one cluster. One cluster is 8 sectors in this example. One sector is 512 byte. We have a file whose data size is 200 and 2050 bytes, and you are supposed to calculate, the total number of slack space. So just following the formula, this one. So whatever is, just have a look at this table, whatever is the total sector size or cluster size, just subtract the total file data from that, and you will get your total slack space. Now that slack space will be a combination of cluster slack, the bytes of clusters that are completely unused, and the RAM slack, which is the maximum bytes that are, like untouched, or that are filled by zeros by the RAM. All right. So what are the challenges that are there when we try to, like recover the data from the Slack space? So the first one is encrypted files. So it is possible that, the file that is deleted, that was encrypted. So if the file is is encrypted, the data that is written on the hard drive will be in encrypted form. So even if we find something in Slack space, it will be encrypted, and we will have to decrypt ourselves. The next thing is, there could be encoding. So we know like different file types, they use different encodings. So in order to get the data, or get the meaning out of the data, we would need to know like which file encoding was used, and we will have to decode those bytes according to that encoding. The next thing is SSDs. So if you guys remember from the SSD, there was something called garbage collection. So the SSD, like all the sectors, are all the clusters that are made available again, like the file is deleted, SSD automatically removes or wipes out all that data on these, all the data that is stored there on those deleted clusters. So if you are using SSD, then there will be no slack space there, or there will be, data in slack space, but over the time, whenever the garbage collection runs, that data will be deleted forever. And the last thing is, this whole operation is very time consuming. You will have to, open each and every file. You will have to find the slack space, then you will have to find, the proper encoding for that. So overall, this step is pretty time taking or time consuming. Next, we have the next file system, which is the NTFS file system. What is NTFS? NTFS stands for New Technology File System. It was developed by Microsoft to supersede the FAT and the HPFS file system. So we don't need to go into HPFS file system. That is not, related to our discussion right now. But for the NTFS, you can just say that it is a newer version or a new file system which tried to, like Microsoft tried to include multiple features, new features in this particular file system that were not there in the NTFS, in the FAT file system. So it is optimized for clusters for up to 4 KB of size. So, 4 KB size is the basic cluster size that you use in the NTFS, and you can increase the cluster size from there. And it provides multiple different features. And one of the most important and most interesting feature of the NTFS file system is journaling. So what is the this feature? So the journaling is the feature in which the system keeps a track of all the transactions, such as file deletion, file copying, pasting, moving a file from one location to another, and so on. So what the system does is that it keeps a track, it keeps like a journal. So whenever you want to copy or move the data from one file to another. So for example, you want to, like you are playing GTA Vice City or GTA 5 or any other game, and you want to move it from say file D to from drive D to drive E. So that file might be, 10 GB or like might have a big size. So it is possible that while that file is moving, while you see that copying operation being done on your PC screen, some unexpected thing happen, like your PC crashes, or like power goes out, or some other form of disturbance. So what will happen in that case if you are not using the NTFS file system is that that operation will not be completed, and you will have to redo that operation again. So even if the file was 99%, like transferred to the new location, it will still be unstable, and you will not be able to open the file or use the file on this new location. So with NTFS, Microsoft introduced the mechanism of journaling. So every time you do any file operation, for example, moving a file, deleting a file, copy pasting a file, and so on, the file system adds this entry, or like keeps a journal of all these operations. So it adds this entry that, for example, I want to move GTA 5 from say drive D to drive E. So first it adds that entry in this particular journal that it keeps. Then it actually starts doing that operation, or then it starts the copy pasting operation. So now if anything happens during that operation, like your system, powers off, or there is some other disturbance during that particular time, and your PC turns off, the next time you start the PC, the file system will automatically look into journal, and whatever were, like whatever you were doing before that crash, the file system will automatically try to recover that. So for example, in this particular case, if the PC turned off unexpectedly while you were copying GTA 5 from C drive to D drive or some other drives, then it will automatically resume that for you in the backend, and you will see the actual process done on the hard drive, and the file will be moved from the original location to the new location. So just to keep in mind, journal is just a record of all the copy pasting, file moving, file deletion operations. And it is specifically very important for files of large size, that when you are doing the operation, delete operation or move operation or copy paste operation, then it like keeps that entry, logs that entry or logs that operation in the journal, performs it. If the operation is successful, then it will just like uncheck that entry or remove that entry from the journal, that that process has been completed. If some mishap happens and that copying or moving the data process cannot be finalized, then the file system will automatically look into journal, and whatever was the last unfinished step or unfinished process in the journal, the file system will do it automatically for you, and you will see the working version of the file in the new location. So journaling is one of the interesting features of the NTFS file systems. There are multiple other features as well that we will discuss one by one. The second thing, or the second main feature and of NTFS, is the scalability. So in case of the FAT file system, we saw that 2 to the power 32 was the maximum number of size of number of clusters that FAT file system can support. In NTFS, we can have 2 to the power 64, around 2 to the power 64 clusters. And if you have a hard drive of say size 256 TB, we can format it using the NTFS file system. So that is the theoretical maximum, the actual maximum, and theoretically you can have around if even if you have 1 billion GBs of data in your hard drive, you can format that hard drive using the NTFS file system, and it will still be able to support that particular hard drive. So scalability is another unique feature of the NTFS file system, or another advantage of the NTFS file system over the FAT file system. So apart from journaling, we have some other features as well. So file compression is another feature, interesting feature. So NTFS allows you, or gives you the option of compressing a file. So all the files that you have, if you have NTFS file system in Windows, just go to properties, right click on a file, go to properties, go to advanced, and there you will see the option of compressing a file. Similarly, we have the security feature as well. So it also provides shadow copy. So shadow copy is basically, like a backup copy or a snapshot of your entire file system at any given time. So you can make shadow copies or snapshots of your entire hard drive in NTFS file system as well. And you can, go back to these backup snapshots or these points in time. Like if anything happens to, some of your files, you can migrate back or go back to these recovery points or these snapshots. Then security is another feature. So NTFS provides you the capability of encrypting files. So you can encrypt individual files in NTFS file system. That is not some feature that is available for FAT. Automatic defragmentation and disk optimization is another interesting factor, or another interesting feature that we will look into in detail. So I'm sorry, like encryption right here, that you can encrypt. Security is that you can set permissions, like you can set which user or user groups have the permission to read the file or modify the file and so on. And lastly, alternative data streams is you can say one of the most trickiest and most interesting feature of the NTFS file system. So you can have multiple data streams within a single file, and you can use these data streams in order to hide data from the user. And this is also very extensively used by the different malwares and viruses. So they reside in the alternative data streams of different files. So we will look into all of them one by one. So we already discussed journaling. For the other things, I will try to show you examples as well, or give you guys a demo as well, like how you can access them in Windows file system. So a couple of NTFS basics. So, and in NTFS, everything that you have is a file. So, the other one had the directory table and other things. In NTFS, everything, all your folders, all your files, all your directories, everything is considered a file. And all of those files, they are in the MFT table. So here we have the MFT table. In fact, we had the FAT allocation table, or FAT table. In NTFS, we have a similar table that keeps record of all the files and folders on your hard drive, and that table is called MFT table. So when you format the NTFS file system on your hard drive, it will create several system files or metadata files, such as the MFT table, which is master file table, and this is an equivalent of file allocation table in NTFS. It will have bitmap, it will have log files and other system files or metadata files. So we'll look into these files as well one by one. So just hang on. This is how the layout of your hard drive will look like. So first, similar to the FAT file system, you will have the boot sector. So this is very important. No matter what file of system you are using, you need to have the boot sector, which will contain the bootloader and the other information about partitions and so on. Then you will have the MFT table. So in FAT, we had the FAT table. In NTFS, we have the master file table, which contains entries for all the different files and folders. Then we have system files. So system files are these things, like the master file table itself is also a system file. We have the bitmap files, log files, we have the volume information files, security files, and so on. And lastly, we will have the file area. This is, these are the unallocated sectors in your hard drive that can be used to store different files. So a couple of changes in the NTFS file system. So in fact, only one sector, the first sector, was the boot sector, and it just contained the information about the bootloader. In NTFS, first 16 sectors, it will start from sector number 0. Again, but the first sector of your hard drive will contain the boot sector, and depending on the size of the boot sector and other information that the file system stores in that boot sector, it can go up till the cluster number 16. So you can have total, like maximum from starting from 0 till 16, so around 17 clusters, for 17 clusters allocated to the boot sector of the NTFS file system. Then you have the MFT, which is the master file table, and this whole thing can take up to 12.5. So generally it is 12.5% of the entire hard drive, and it can go up to the 50% of your hard drive can be just occupied by the MFT, and then the remaining 50 will be available for you in order to write different files. So this is how, this is the difference between the different number of clusters and sectors and the cluster and sector sizes. So depending on the size of your hard drive, for example, if you have a small, say, memory card or a flash drive, say, less than 1 GB or 2 GB and so on. So as your like hard drive or storage devices size increase, the cluster size, like how many sectors are there in one cluster and what is the total size in kilobytes of that cluster, also varies. So it is optimized for 4 KB cluster size, so total 8 sectors in one cluster, but it can change for files storage devices that are more than 16 TB and above that size. So up till 16 TB, you have 8 sectors per cluster, and one cluster is 4 KB. But after that, you see that the cluster sizes increase and the number of cluster as well increase as the size increases. All right. So we talked about, NTFS file system creates different various files or system files or metadata files on your hard drive. So let's look into them one by one. So similar to FAT file system, where we had two entries or two mirror copies of the FAT table, in NTFS file system, we will have two copies of MFT or master file table. So both MFT and master file MFT2, which is a copy, they both are used to store, like records for different files. So all the files that you have, files, folders, directories, whatever, that will have one record on this MFT table. And this is how, like the description of these entries, and this is how these entries can be like found. So all of these system files, they begin with this $sign. So $MFT means master file table. Then we have a mirror copy, which is MFT2. Then we have the log file. So what is log file, or what is this data structure? So log file is basically what we talked in the journaling, that NTFS keeps a record of all the data moving operations that you want to do on your computer before it starts that operation. So log file is actually the location in which it stores that information. So whenever you move a file, an entry is created in log file telling or noting the moving operation, and when that operation is done, that entry is marked completed, and you can move on to the next operation. Then it has another metadata file which is called volume, and this contains the information about the volume, like if you have different logical drives, their names, and also the name of your hard drive and those type of things. Then we have another interesting thing, like the root directory in NTFS file system is just represented by the $sign. So it tells you where the root folder is in the NTFS volume. So similar to FAT file system, we will have to, in order to find the information like where or which entry in the MFT table represents which file, we can go and look into the root folder. Then we have the bitmap. So in FAT file system, we had this information, stored within the entry. So let me just show you quickly. So right here, this busy bit. So in FAT file system, we had that one bit in the file entry itself that told us that, whether that sector is available or for writing, or whether it is busy or used by some other file. In NTFS, we have another region and another, entry in our hard drive, which is called bitmap, and bitmap contains the information of all the sectors. So it tells us that which sector are busy, or which sectors are busy, and which sectors are available for writing the data. Then we have another thing which is called bad clusters. So similarly, over time, some clusters in your hard drive, some look, physical sectors in your hard drive, they can go bad over time, and they can become unstable. So when they become unstable, we want to avoid writing data in those clusters because there's a chance that the data will be lost forever. So there is another metadata file called bad cluster, and this contains it is a map of all the clusters that have gone bad. So for example, if cluster, say 120, 550, 617, they are all gone bad, that will be noted in this bad cluster metadata file. Then we have the secure file, and it is for the security of individual file. So it will have an access control list, like which of the user groups on this particular computer are allowed to make changes or modify or delete data in this particular file. So that access control list, which is a security feature that NTFS provides, that is managed, or that is stored in this security file or secure file. So these are the main important ones, like MFT records or metadata files that you need to remember for your exams as well. So bitmap, bad clusters, secure, what these three things are. Then on this slide, what is an MFT, what is an MFT mirror, log file, what entries it have, what it is used for. It is used for storing the journaling information, and the volume metadata or system file, which contains the information about the file system and your hard drive. So this is how one entry in an NFT table will look like. So you can see that it starts the first like every folder or a file. It is considered as a bunch of different attributes. So you have all these different attributes. So you have standard information. It is one attribute, file or directory name, another attribute, security descriptors, the third attribute, data or index, the fourth attribute, and so on. So in this way, you can have, one file or a folder as a combination or as a group of different attributes. The total size of one entry in the MFT record is 1001 KB or 1024 bytes, and it can consist of multiple attributes. So standard information, metadata, when the file was created, last modified, those type of things. That is the very basic attribute of NTFS of any entry in the MFT table. Then you will have the file name, for example, file.txt, like directory foo, or say like PowerPoint.ppt, or whatever file you have. That information or the name of the file will also be an attribute in the MFT record. Then like all these records that or attributes that are there on one MFT entry, they can be categorized into two things. First are called resident files or resident attributes, and the second are called non-resident files or non-resident attributes. So how do we determine which one of these attributes are resident and which one are non-resident? So as I mentioned earlier, like the maximum size of this one MFT record for one file is 1 kilobyte. So if your overall file size, like file name, file content, file metadata, and everything else, all of that is less than 1 kilobyte, then all of these attributes, they will be present on the MFT table. So all the attributes that are present on the MFT table, they are called resident attributes, and the files that completely reside in the MFT, like all the information about that file can be found in the MFT record of that particular file, that are called resident files. Now, sometimes it can happen, the data part is something which can vary, right? You can have one text file with just your name, or you can have a text file with your, say, final report or with your master's thesis, right? So that file will be hundred of pages, that document will be hundred of pages. So you cannot store hundreds of pages of data in 1 kilobyte, right? So then some of this data will be stored in the other halves, or say other sectors in your hard drive, and the pointers to those sectors will be stored here. So if any attributes content is stored somewhere outside the hard drive, or some on some other clusters on your hard drive, and just the pointers are available there, then those attributes become non-resident attributes. So there are two type of attributes: resident, which reside on the MFT record, like completely reside on the MFT record. So standard information and file name, these are generally resident attributes because they are there on the MFT record. Then data is one attribute that can either be resident for very small file sizes. I've just it's just one like character or two characters or one sentence in your txt file or document file. Then all of that can be stored in the mft record. It will become a resident attribute. Otherwise, if the file size is bigger, then we will have to store it somewhere else in the hard drive, and we will just store the pointers to those sectors over here in the data attribute, and this data attribute will become non-resident. So this is like, very important classification, resident attributes and non-resident attributes. So please, like, I might ask that in exam as well. It is an important topic, so keep in mind. So this is like, an illustration of the MFT table. So all the things, or, like if you format your hard drive with the NTFS, you will have master file table. So the first two entries in the MFT are the MFT itself. So it is, like all the information about different files. Then you have the log file, you have the volume file, you have the bitmap, boot, you have the bad cluster, you have the reserved. So reserved is basically, like clusters or sectors that are reserved for different system operations, and they are not available for user. And if you look into the record of an individual file, for example, like this is our file txt from the previous example, then the first attribute will be standard information, creation time, deletion time, those are not the deletion, like creation, modified, last access, those type of things, like the metadata about the file. Then you will have the file name as another attribute, and then we will have the data. So data streams, so like data is written in the ntfs in the form of different data streams, and these data streams, they can be either resident if the entire data is stored on this particular mft record, it is less than 1 kilobyte. If it is bigger, then we will have to like store it somewhere else on the hard drive, and just put the pointers to those sectors, just store the pointers there in this data attribute. So this just shows you the, like resident and non-resident attributes. So standard information, file name, all of them, they are resident attributes, and then data streams and some other attributes, they can be non-resident or extent attributes, and their pointers are just stored here in this particular MFT record, and the content will reside on some clusters outside in your hard drive. All right, so this is just like, the information, like how, what are the resident and non-resident attributes. So if your data, the file content is larger and it cannot be stored in 1 kilobyte, then you will have to allocate some set of clusters outside in your hard drive, and then just store the information, or say the pointers to those clusters in the data attribute. So when you are allocating clusters to, like your file, so you cannot maybe, have like individual clusters, because for example, if your file consists of say 100 clusters, so will you have 100 entries in your data attribute? No. Why? Because it will become highly inefficient, and we will, like it will require a lot of space in order to write the pointers or the cluster numbers for all of those records. What happens in fact is, whenever the file system allocates clusters to one particular file, rather than allocating clusters individually, it tries to find clusters that are physically, closer to each other, or they are physically neighbors. So for example, rather than having individual clusters, we provide something which we call data run or cluster run. So cluster run is basically a set of multiple clusters. So you can think of it as a linked list. So if this whole cluster run or data run, run list or data run is allocated to one particular file in order to store data, then we will just write the starting or the head of this cluster run or data run in the data record, and then we can just follow these clusters, these, one by one, in order to read or write the data. So for small files, like, for example, this is a example of small file record. If the total size of the file, including the name, the metadata, the content, and everything, if it is less than 1 kilobyte, then that whole file will be on the MFT table. For larger files, some attributes such as the standard information, name, and so on will be there stored in the MFT record. For larger attributes such as the data, we will have the starting pointers to these different data runs. So for example, in this case, this file is large enough and it is, like stored in these particular different data runs. So we'll store this information right here. So an example of this would be, for example, this cluster right here, the first one is 100, and it has say 20 clusters in this particular data run. So we will have in the data record of a large file, we will have the first pointer to this first data run. So we'll store, cluster number 100 and go or read next 20 clusters. Then we have another data run right here. So we'll just write the starting cluster of this data run and how many clusters are there in this data run. So the second entry of your data record will be the pointer to this head to this second data run and how many clusters are there in this particular data run. Then similarly for the third one, we will just store the first or the starting cluster pointer in the data attribute, and we will add like how many clusters are there in this particular data. So total, we will have just 3 starting pointers or 3 clusters, the head clusters stored in the data attribute, and we can just follow these data runs when we want to retrieve the data. So these are all the attributes of the individual file. Like, we just discussed like a couple of them right here, like the name and, standard information, security descriptors, data. These are the important ones, but there are so many other attributes as well. And this is like a complete list of attributes that you can look into. So you have this file name, standard information. We have the volume name, security descriptor. This is the data. So it is the, file data for resident files or data runs, or say, the starting clusters of the data runs for the non-resident files. Similarly, bitmap and other information is already there as well. So this is how, the MFT table looks like. So whenever you want to store a file or write some data on a hard drive that have the NTFS file system, the OS will communicate this information or give this request to the file system that I need to, like store file or store data on the hard drive. The NTFS will create one entry in the MFT or master file table for that particular file. It will store its information, the metadata, it will store its file name and those type of things. And it will store the data into different clusters as well. If the data is small, then all of that will be stored in this MFT record. Otherwise, it will allocate some external clusters for that particular to store the data for this particular file. And whenever the NTFS file system is, like allocating these clusters to different files, it will improve or it will update its bitmap. So it will say that, cluster number 100 to 120, they are allocated for file 1. Clusters number, say, 200 to 256, they are allocated to file 2, and so on. So it will update the bitmap as well. All right. So another thing is like what happens when you delete the data from, like, or delete a file in the NTFS file table or in the NTFS file system. So what will happen is, like the file system will, similar to the FAT, it will mark this MFT entry as deleted in the MFT record. And it will, like, all these clusters that were allocated to this particular file, it will make them available again by changing or making changes in the bitmap. So if it previously allocated some clusters to one particular file, in the bitmap, they will be, they will appear as occupied. But when you delete it, they will become available again for writing the data. But the data of that particular file will still be there. So no matter if you have the FAT file system or if you have the NTFS file system, if you are using the magnetic drive, you will still have the Slack space and the data in Slack space available that you can retrieve. All right. So another important, like feature of the NTFS file system is the defragmentation. So before into like talking about the defragmentation, first let's see what fragmentation actually is. So just take a look into this before figure, and you can see that it has these different sectors that are colored differently. So you have blue, you have green, you have yellow, and so on. So what happens is when you create a file, you just like started, say, my project report .doc file. So the file system will traditionally or initially allocate just one cluster to store the data for that particular file. And as your file grows or it keeps growing, you keep adding more data in that file. The file system will have to find empty clusters or available clusters in the hard drive, and then allocate those clusters to this particular file. So it is not all the time that you will find clusters that are adjacent to each other. So practically, this is what happens is maybe like when you created the file, just this particular cluster right here was allocated to this file. Then over the period of next like 1 week or 1 day or something like that, you added more data. Now file system found out different clusters that are physically placed in different locations on the hard drive, and it allocated those clusters to your report or to your file. Now if you want to read the data, or say you open this file, the hard drive will have to read the data from all of these different clusters or different sectors that are scattered on your hard drive in order to give you the complete view of the file. And as you can realize from here, that if you want to delete the data, read the data from these different clusters or these different sectors that are scattered throughout the hard drive, it will take a lot of time. For example, like you will have to read all of them one by one. So over the time, as like you keep adding data on files, you keep like adding new files in your file system and so on, your disk will become fragmented. And in order to like it will have different fragments of a file placed or stored in different locations on your hard drive, and in order to retrieve it, it will require more time. So over the time, as these fragmentations increase, the read speed or write speed of your hard drive will slow down. So in order to avoid it, or in order to correct this, NTFS provided a mechanism which is called disk defragmentation. So this is a mechanism, or you can say a process that happens inside your hard drive without your knowing or your knowledge. It is a background process, and over the time, say maybe like after 1 week or after 2 week or whatever frequency is set in the firmware or in the NTFS file system, the NTFS will automatically defragment the file, and it will move data from one cluster to another, such that like all the clusters or sectors that belong to one file, they become physically neighbors or physically adjacent to each other. They are stored in the same location or in the same region of the hard drive, so that reading a file or writing the data on a file becomes much easier and much less time consuming. So this is the data defragmentation, that over the time you will have different fragments of files stored into different physical locations in your hard drive, and that will slow down the overall reading and writing process. In order to correct it or optimize it, the NTFS will automatically do the defragmentation, and it will like bring the different fragments or different clusters of one file closer to each other physically on the hard drive. So the overall reading and writing operations become faster. All right. So what are the implications of the, or say, what can go wrong with data defragmentation in terms of digital forensics is that if the data defragmentation happens, then, like when the file system is moving data from one cluster to another, it is possible that it overrides some deleted data. So it can override slack space as well. So this whole operation is similar, or you can say, to some extent, it is similar to garbage collection, that over time, like once data defragmentation happens, there is a chance that if any sector, like if the data was there for some deleted files, it will be deleted or overwritten forever. So for example, right here, so you can see these in the before figure, this sector right here is unutilized, or it's empty in the eyes of the file system, but maybe this sector right here contains the information of a deleted file. But now, since it is overwritten by the red file, then that data or the deleted data or the slack space data, it is gone forever. So that is one implication or one drawback of data defragmentation when it comes to digital forensics. All right. The next interesting feature of the NTFS file system is the encryption. So NTFS provides you the opportunity to encrypt the files, individual files, and it uses EFS, which is its own encryption mechanism. It is a public-private key method with which it, encrypts a file. And it also provides you another capability or another option, which is recovery certificate. So what happens is, like an individual user can encrypt a file. For example, you hire an employee and he's working on very critical data that is important to your company. And somehow when you fire that employee, then before leaving, he just encrypts all your files. So what will happen in this case is that if you don't know the key, then you will not be able to decrypt these files and get your data back. But NTFS, in order to avoid such circumstances or such scenarios, NTFS also provides you with a recovery certificate. So the admin of your company, or like the administrator of your organization, they will have these recovery certificates, and these recovery certificates, like, they act like a super key. So even if one particular user, like, encrypts the data with its own private key, if that user leaves and it doesn't provide you that private key, the admin of your organization, they can use these recovery certificates or these super keys in order to retrieve the data. So this is a feature that is provided by the NTFS. Like, you can encrypt individual files with any key that you want or any password that you want, and the administration, or like the admin of the company or the owners of your like PC, they have these recovery certificates that are super keys that can unlock or break that encryption. All right. So this last feature of the NTFS is very, very, very interesting, and it is, one of the feature that is extensively used to hide the data. It is also used by the malwares and viruses in order to hide the executable part, and this is called alternative data stream or alternate data stream. So in the NTFS, you have multiple data streams. One file can have multiple data streams, and like the data attribute that we saw, rather than having one set of clusters, it can have multiple set of clusters or multiple data runs for each of these individual data streams. So by default, we don't give any name. Like, when NTFS stores some data, the data attribute will just have one data stream which doesn't have any name, and it is also called unnamed data stream or the default data stream. So this data stream is the one which the NTFS uses to retrieve the data generally. And if you look into a file, you will see this data stream as well. Like, if you double click on the file, the NTFS will go onto that MFT record of the file, and it will just retrieve the data that is there in the unnamed stream or the default data stream. But there can be hidden data streams as well that you can, like, create, and you can hide data in them as well. So in the data record or the data attribute, you can actually see that as well, that this data attribute, it can have multiple streams. So the default stream is not named, but you can create alternate data streams in one file as well. And how you can do that, just like put a separator, a colon here, and then write the name of the other stream that you want to create, and you can put the data, or say malicious data, in this hidden stream, and keep it hidden from user size forever. So for alternative data streams, you have to provide the name. The default is unnamed. Like, if you don't provide any name, then it will become the default stream. So this is how you can illustrate this whole thing, or this whole concept, that this is how the normal data attribute looks like. So you have just one, like a stream, or say one set of clusters written here, or data runs written here, that are your default stream. And this is what will be visible to the file system, or what will be visible to the operating system. But inside this data attribute, you can have some hidden streams as well. So you can create as many streams as you want, and in those streams you can have other data runs, or say run lists, or other set of clusters that contain the hidden data. And you can, like, name these streams like stream 1, stream 2, stream 3, and so on. And these will be visible to the file system only, but from the user perspective, the operating system will not be able to see that. And even if you open these files, say like you are observing them in Explorer, you will not be able to see these streams, and they will not, like, even you will not find the size of these streams as well. So all the attributes that you see, they will be that will be of the unnamed or the standard data stream, or the, like, uh, the default data stream. So this slide is for you guys in order to, like, do the actual demo. I will show you this demo shortly as well. So if you want to say like, for like write some data in an alternative data stream. So we have this file example.txt. It is a benign file, and we want to hide this data or this text, which is this is hidden, or you can have any text or sentence here. And what we will do is we will create an alternate data stream here, which will be which we will name as hidden.txt. So this is the command. So just open the terminal in your Microsoft Windows, and then just type echo the text that you want to hide, the basic file in which you want to hide this data, and then the name of the stream that you want to give to this particular data. So you can store or you can hide text data, you can even hide image files, video files, you can even hide executables as well into a text file. So that's why I said, like, most of the malwares and say viruses, they hide their executables in benign files. So maybe, from the outside you just see that, oh, I'm like downloading an image file or a text file from the internet. But it is possible that in the alternative data streams you will see that, like some people might have malicious executables stored there. And you can use like third-party tools too in order to, add these streams in a file or retrieve these streams. But generally you can do it by using these commands as well. And when you want to view the data from this particular stream, you can use the more command. So more, then this greater than sign and example.txt, like the file that you want to get the data from and the stream that you want to read. So if you don't provide any name here, it will read or retrieve the data from the default stream. But if you have some hidden stream in a file, then you can get the data from that hidden stream as well using this command. And if you want to list like, the all the streams that are there in one particular file, just use this dir command and you can do that. So let me show you guys a demo of this. All right, so let's see a demo of the alternate data streams in Windows. So I'm using a virtual machine with the Windows operating system running, and I have NTFS file system. So before we go into the the alternative data streams demo, let's see the other features that we just discussed. So if you just right click on properties in any file, you can see, go to advanced. And over there, you can see that you have these options of compressing the content. So you can compress a file in NTFS file system, as well encryption. So encryption, you can also encrypt the content of the file using any password that you want. Another interesting feature is like if you go to security, you can see that there are different user groups that are, like running on this PC. So you have system, you have like the user, and you have also the administrator, three different user groups. And then over at the bottom, you have the different permissions. So all these different groups, you can assign them different permissions. And if you want to like, restrict somebody or some user from accessing a file, you can select on that particular user, and then you can just like, modify these permissions and maybe, stop somebody from writing content on this file or modifying this file. So using these different features in the NTFS, you can secure a file, you can compress a file, and you can also maintain an access control list. So let's move on to the next thing, which is the alternate data stream. So I have two files, like I have this example txt file, and if you open it, you will see that you just see this one line right here. This is an ADS demo file. So this is basically, this data is in the default stream of this particular file. So let's go and look into that. So for that, just I open the command prompt in this particular folder right here. And then you can see like, come here. We want to see what are the different streams that are there for the example.txt file. So for that, we will use this command dir/r and then the name of the file. So it is the example.txt. So right now we just see there is just one data stream which is unnamed. If there was like, any name here or any other stream, then it would have a name. So the unnamed stream is the default stream and it has 23 bytes of data. So now let's hide some data in this particular file. So for hiding the text data, we'll use echo command. Echo, this is a virus. So you can type any text that you want to hide. Then we will use this greater than sign, then tell in which file we want to hide this data. So we want to hide this data in the example.txt, right? then put colon, and then give this particular alternative data stream a name. So let's call it virus demo, right? So just do that and press enter. Now, if we open this file again, we don't see this text that we wrote here because the operating system just looks at the default data stream or the unnamed data stream. So let's go here, see if we see that data stream in this particular file. So using the dir command, we can see that now we have created another file or another data stream in this example.txt. We called this data stream, we named it as virus demo, and this stream has total 18 bytes of data. So as you can see, like from the this thing as well, if we look into properties like the simple explorer, we still see that there is no issue, or this additional bytes that we just wrote, it still doesn't appear, and the operating system just shows you that it is 23 bytes, which is the original byte size. So no matter how much data you hide in the alternate data stream, that will be not visible to the user. Now, if we want to see this data, what we need to do is we can use the more command. So more less than sign, then the name of the file, example.txt, colon, and the stream that we want to read. So if we don't provide it any stream, it will give us the data from the unnamed.default stream. But this time we want to get the data from this virus demo stream, right? So just type virus demo, press enter, and you can retrieve the data that you just hid in the alternate data stream. So it is not just text files or text that you can hide. So let's clear that. You can also hide images or videos or even executables in the alternative data stream. So how we can do that? For that, we need to use type command. So type name of the file that we want to hide. So right now in our folder, as you can see, we have an image file, which is image.png, because type is png. So we want to hide this file. So say we want do the type command, then type the name of the file that we want to hide, image.png, greater than sign, the file in which we want to hide it, example.txt, colon, the data stream. Like now we will have to provide it a name. Now we can, either update the virus demo stream, or we can create a new stream in which we can say hidden image. All right. We name this data stream as hidden image and press enter. So even though, this file is 205 KB, you still don't see any change in the example.txt. It's still showing you that it is, like 1 KB, because that's the smallest size. In reality, it is still 23 bytes. So this way, you can hide or create as many alternate data streams as you want, and you can hide executables there. You can hide videos, images, text files, whatever you want to hide there, and that will not be visible to the operating system. And even if as a forensic investigator, if you are looking at these files, you will not be able to see the alternative data streams. That's why it is very important that whenever you guys are investigating a file, you also need to look into the alternative data streams. And how you can do that: in Windows, just use this command dir/r, and then write the name of the file. So right now I am in this particular folder, so I just have to write the name of the file. If you are, say, in some other location, you will have to give the complete path of this particular file. Press enter, and you can see that this is the unnamed data stream, which is the default data stream. It is 23 bytes. Then we have another alternate data stream called hidden image, and it has the whole image that we just hid in this particular file. And we have the third stream, which contains our text, which is named as virus demo. So in this way, you can hide as many data streams as you want, and you can hide all sort of different type of data in there. So coming back here, you can hide executables as well. So this is how you can hide the executable, and once you hide it, this is how the command at the very bottom, this is how you can run the executable file from a hidden data stream. So this is very useful. Most of the viruses, malwares, they use these techniques in order to hide the malicious executables in benign files, and then run them from those benign files. All right. So the next question that might come in your mind is that what is the use, like what is the proper use or benign use of these alternative data streams? So before we jump into that, I assume most of you guys have experienced that whenever you download some say program or some other file from the internet, and then you later on try to open that, when you double click on it, Windows sometimes gives you this error that this file or this software is downloaded from some untrusted source, right? So how does your operating system knows that which like website or which whether the source from which or the website from which you downloaded this particular file, whether it is trusted or not? So what happens is whenever you're using Internet Explorer or Chrome or Firefox or any other browser, whenever the browser like downloads a file, it uses the alternative data streams in order to store this additional metadata. So for example, this is the benign use that you want to store additional metadata that is not related to the file, but it is just like maybe some safety mechanism or security mechanism or just a warning mechanism that the Internet Explorer or any other browser wants to give you whenever you try to run the executables. So when you download a file, your Internet Explorer or the browser will put the information of the website from which you downloaded that particular file in the alternative data stream, and then when you try to run it, you will see that error. All right, so this is the benign use that it is used to hide or store metadata, which is not directly linked to the file, but it can be, like where you downloaded the file, who's the owner of the file, those type of things. And the malicious use is that it could be used to hide the data. And, like it is very popular for hiding malwares and viruses. And you can also like hide executables in the alternative data stream and run the executables from the alternative data streams as well. So this is something that whenever you are doing forensic investigation, you have to pay attention on the alternative data streams, and this is like one fundamental step that you have to look whenever you are investigating any particular file, that see if it has alternative data streams. All right. So the last thing in and the NTFS is like, what happens when we delete the file. So the mechanism is same as FAT. When we delete the file, the MFT entry of that particular file is marked deleted. Then, like the bitmap, which contains the information of the clusters, like, the clusters that were associated to this particular file that you just deleted, their values will be changed in the bitmap. And if it was one or say occupied before deleting, now they will become available again, but the individual data of that particular file will still remain in those clusters unless it is updated or unless the defragmentation happens or by default. So this is the mechanism to delete them. All right, so this concludes our discussion for the file systems. We discussed the NTFS file system as well as the FAT file systems. What are their features? What are the important features of NTFS? It is way more advanced as compared to FAT, and you have other like so many important things such as journaling, defragmentation. You have like the alternative data streams. All these topics are very important for digital forensics and also from the exam perspective. All right. So the next thing is Windows registry. So let's see what Windows registry is and how, or like for what it is used for. So before we jump into that, like just keep, like have the scenario in mind that you are working in a company and you see one of your coworkers plug in a USB drive, and then he copies some important data that is related to your, like say, some trade secret or something like that in that particular flash drive or the USB drive, and then just leaves the office and, just like resigns from his post. Now, if you want to investigate this particular case, then you need to somehow figure out that whether the user actually plugged in the USB drive in your PC or not, or at what time or what USB drive did the user plug in into the PC in order to copy or in order to steal the data. So can you guys just like take some time and think of some location or some artifact which can give you guys this information about the hard drive that you or the sorry USB drive that the suspect might have used. So none of the artifacts that we have discussed so far, like the file system or say the extensions or hidden alternate data streams or journaling, whatever we discussed so far, none of them will provide you that information. The only way that you can get this information is from Windows registry. So what is Windows Registry? Windows Registry is basically a database that is, incorporated in Microsoft Windows, and it stores the information about the user, about, like the user preferences, about the system settings, about, the softwares that are there, about the hardware changes that you make in your system. All of that information is stored in the Windows Registry, and it is a hierarchical data structure. So you have five basic folders or five basic registries, which are also called hives. And inside those hives, you have so many different, subfolders, and they are used to store all kind of different data about the user, about the system, about the hardware changes, and so on. So these are the five main hives that I mentioned, or the five basic folders in the Windows registry. They are also called the hives or the main folders of your Windows registry. So at the very first, you have this hive which is called HKey classes root, and this stores the information about the different programs that you have, the different files that you have, and the extensions and which programs or applications should be used in order to open those files. So if you guys remember from the file extension lecture, we talked that this information that which application should be used to open, say, Word files or PNG files or JPEG files and so on. So that information is stored right here in this root registry hive. Or say directory that provides, like, if you have a document file, use Microsoft Word. If you have an Excel file, use Microsoft Excel, and so on. Then you have another registry or another hive, which is HKey current user. And this contains or stores the all the preferences or settings of the current logged on user. So for example, if it is a public PC or if it is a company PC, multiple people might have been using that, and each of those people have their own preferences, right? What background you want to have, what, like, whether you want to have like large icons or small icons and those type of things, or all other user related settings. They are stored in this particular hive, which is HKey current user, and as name suggests, it contains that information about the current user. The next thing is the local machine. So this particular hive contains the information about excuse me, this information, it contains the information about your system. So all the hardware related things, like hardware changes, whenever you plug in a USB drive, the data is stored here. Whenever, like if you have an external drive, or if whenever you connect to the internet, like you make Wi-Fi connection, all those things, they are stored in the local machine hive or HKey local machine in your Windows registry. And if you just want to, like find the configurational changes, or the settings of your PC like as a whole, that you can find here in the local machine Windows registry. The next one is users. So this contain profile of all the users. So for example, if there are 5 users that log in on one particular PC, there will be 5 entries, or user entries, or 5 subfolders in this particular registry, that will tell you that how many users are there. It will tell you the information that how many times each user like logged into on this PC, when was the last time they logged in, and so on. Lastly, you have the current configuration hive, or say like registry basic folder, and this contains the information about or the configuration of the hardware of your overall machine at the startup. So this contains which say applications you want to run when your PC starts, like which application should go into auto run mode, or like they should start working as soon as the PC starts, and so on. So all the hardware profile of your PC at the startup, like what configuration or settings or applications you want to run at the startup, that is stored in the current configuration hive. So this is how a registry looks like. It is just like shows you a screenshot of registry editor. I will show you a demo of this as well, so don't worry. So this is basically the key pane where you have all these keys or all these basic 5 hives. So you have 5 hives in total. And if you click on any one of them, you will see these subfolders or sub keys. So these things are called keys, like the basic directories that you have. And on the other hand, this is the content pane, and here you will see the different things as value. So for example, all these 5 big folders or hives, they are the root keys or root hives, and if you go down, open any one of them, you will see these subfolders, and these, all of them, they are called subkeys. So if you click on any of these, you can see that you have a different content pane for all of different one of them. And this is like stored in the form of key and value. So your keys are here and their actual content or their values is here. So this is the value name. So you can have multiple values for one folder or one key, and you can see like all these different files here, the name of the file and the data that is there on each particular file. All right, so now let's go back to our previous example where we wanted to, examine the case where a suspect plugs in a USB drive onto a computer, and he like downloads or stores, like copies different files that might have been very important or trade secrets into that USB drive and then goes away. So in order to find that, the first step that we can do is we need to know the history of all the hardware changes. And whenever you plug a USB drive in, it is a hardware change. So the H key local machine, so this is the complete address. So, in the previous example, so you can just reverse this hierarchy, go into like, these different folders, go to the local machine, then go to system, current control setting, enum, and then over there you will have this USB store or this USB folder. And this contains all the information about the different USBs that you have plugged in into your PC. And this information stays there for a very long time. So, whenever you plug in a USB, the information of the USB, like when did you plug in that USB, what was the manufacturer of the USB, if that USB had like any name, what was the name of the USB, and so on. All of that information will be stored here. Another way or another location to find this information is the mounted drives. So this is like, if you just follow this complete hierarchy, this is the key that contains the information of all the mounted drives and what were their letters. So every time, like you mount a drive or you mount a USB or attach a USB to your PC, it will be shown as H drive or I drive or something like that. So what letter was assigned to that will be found here. So in this USB store, key, if you look into the data of that, you will find device serial number. So all the USB devices that you have, they have a serial number. So that is assigned to them by the manufacturer. So if you wanna pinpoint that, later on, for say police finds that USB drive, the physical drive from the suspect, then you can look into that device serial number and go and explore the USB store and find if any of the USB entries there match the same serial number or have the same serial number. Similarly, we have the recent files. So, whenever you open a file, you close it. Windows maintain a history of all your open files, and it stores that history into this particular registry key. So just follow this path in the Windows registry and just follow it, and you will see all the recent files that you might have opened. Lastly, the active user, we also want to make sure that, when this whole copy pasting operation was being done, even though we have found the USB drive that was used to do that, we want to link it to that particular suspect. We want to say that, say John did that. So for that, we have to make sure that, we have proofs that John logged on into the system. So where we can find that, we can go into local machine software, this particular key right here, and it will contain logon UI, and it will contain the information about, which users logged in on this particular PC at what given time. So from here, if we see John's login ID, we see, like John in the recent file subkey, or in this particular key, we see that, trade files or trade secrets file was opened. And by comparing all these things, combining all these things, we can also say that, this file, John logged on at 3 p.m. He opened the files, trade secret files at 3:15 p.m. At 3:10, he attached this particular USB and then copied the data. So combining all this information, we will have concrete proof that John actually did steal the trade secrets by just copying them on the USB drive and leaving. So apart from that, this in bold is, contains the information or say the important things that you can find from the Windows registry. So Windows registry is like, just like volatility, it's a field in its own. So we will have one lab on that where you will have to find different things from a Windows registry. So we will do that hands-on experiment as well, or demos as well. But from a few things that you can remember is that you can find the USB storage devices that have been connected. You can find the recent documents, like which documents or files were recently opened. You can even find the typed URLs. For example, whatever the user types in Internet Explorer, that is saved in the typed URLs registry key in the Windows registry. You will also have like every time you connect to a Wi-Fi network, that is also stored, or that information is also logged, and you can have the list of all the Wi-Fi connections that this PC might have connected to if you just follow this Windows registry. And lastly, the startup location. Where do you find the all the startup like auto run uh, applications and so on? So just follow this particular thing, current version run, and over there you will find all the different applications that are in the auto run mode or that start whenever the PC starts. So the last thing is the prefetch files. So every time you open an application, say, or open a program in Windows, the first time when you open it, or every time when you open it, that particular application will have to say, get some DLL files, or it have to say, get read some data that might have been stored somewhere on the hard drive in order to start, or in order to operate. So what happens is whenever you open a file for the very first time, window creates, or an application for the very first time, Windows create a prefetch file for that particular application. And in that prefetch file, Windows stores like all the information, or say prerequisites, that particular application needs in order to function properly. So for example, if your Microsoft Word .exe, which is the Word application, if it needs, say, some certain DLLs, or it needs some certain other data that might have been stored somewhere else on the hard drive, so Windows will get all of that information and create a prefetch file for that particular application. So the next time you open that file, Windows will not have to go and search for the different data components all over in the hard drive. It will just look into the prefetch file and give you all the basic requirements or the prerequisites that this particular application needs in order to start. So this was introduced by the Windows XP, and all the later on, like Windows versions, they all have this prefetch file system available to them. So it is just basically these files, or this whole mechanism was created to optimize the application startup. So the application will take less time when they start, because all the data that they need, that is available in one single source, which is the prefetch file. So whenever you double click on an application, the Windows will just read its prefetch file on the hard drive, and it will just like give it all the resources, or say DLLs or other things that it needs in order to work properly. And every time you open the file, or sorry, or run the application for the very first time, this prefetch file is created. And the next time you do some operation, or you start your application again, then only some of the things in this prefetch file are modified. But every time when you run the application for the first time, Windows will create a prefetch file for that particular application. So what does this prefetch file contains? So it contains metadata, like, what is the name of the executable, how many times you run this executable, how many times have you, run this application on this PC, where in hard drive, or where in your PC this particular application is stored, what is the size of the prefetch file. And it will also have important timestamps, such as when was the last time you run this application, and when was the first time this application was stored, the first time this prefetch file was made, and so on. So as you guys can see, this is very important information from forensic perspective. We can not only find when was the last time any application was started by the user, or was used by the user. We can also find like the total number of times the user used it, when the user first downloaded that file, and when the prefetch file was created, and so on. So again, like from digital forensics, when we are investigating any particular application or any particular device, we also need to have a look at the prefetch files, and it can give us like all this important metadata and timestamp information that can be beneficial for our particular case.
So this is the end of the lecture for window forensics. So we have covered the structure of the file system of the hard drives, of the HDDs as well as the SSDs. We also talked about the different features of NTFS file system as well as the FAT file system. So all of them are pretty important. So from exams perspective, so pay an important attention on them. We also talked about Windows registry, what it is, what type of information can we retrieve. So this information is pretty important. So just keep in mind that what we can retrieve and from where we can retrieve that. So you don't need to remember the whole path, just remember maybe just the last folders or the last key names where you can find that information. And lastly, we talked about the prefetch files, why they are there, what is their purpose, and what type of data we can get from them. So before ending, let me just show you where you can find this prefetch files. So if you are using Windows, just go to C and go to Windows folder, and over there you will see a folder we called prefetch files. So let me see here. So right here, prefetch. So if you open it, then it contains the prefetch files. You can see that it has created prefetch files for all the different applications that are there on my PC. So some of them, the very first one, FTK Imager. So I've been using FTK Imager a lot. So it has created the prefetch files for different things. One thing to remember is that one application will only have one prefetch file, and the different things that you see here, they might be different, maybe the one should be for the executable, or say the application, and the other one should might have been for the installer and so on. So if you just double click on this file, it asks you which program you want to open it with. So if we open it with Notepad or any other thing, we might not be able to see any important data. It will be just gibberish. You can't make any sense of it. So for that, you have external tools. So this is like Win Prefetch View. It was an open source tool, very small, that I just downloaded a few minutes ago. And if you open that, it gives you all the prefetch files that are there on your PC. And if you look at the access data FTK imager, it tells you the created time, when was this prefetch file created. It tells you the modified time, when was this file last modified, the file size, like what is the total size of prefetch file, process executable, like where is the executable for this particular application. So the process executable name, its complete path is available, the run count, like how many times I have run this application. So every time the prefetch file is created, the default will be one, because it is only created when you run the program for the very first time. So you can see here 111, and for some one applications you see like 4, and you can see multiple run counters as well. So this tells you that how many times a user has executed or started this application. Then over here, you will see last runtime, which tells you that when was this application last used. So all this information, all these important timestamps, when you was this prefetch file was created, that tells you the first time that application ran. The last time that application ran gives you the latest execution of that particular program. You can also find how many times the user ran it and where to find the executable and what is the name of the executable. So this is all for the prefetch file. For window registry, if you have using Windows 10 or any later version, or I think even 8 as well. So just go to the setting and just Windows and just type registry viewer. So just click on that and it gives you, or it opens up this application. So this is the application that you guys saw in these slides as well. So you have these 5 basic hives, or 5 basic keys. So we have the root, current user, local machine, user, and current configuration. So we can explore all of them. So all of them, it is a hierarchical structure, and there's tons of information that you can find. For the USBs, a particular example, so just go on the local machine, then look into system, then go to enum, and in enum, sorry, in system you will go, then next one is control set 1. So you might have multiple control sets, control set 1, control set 2, control set 3, and those type of things for different users and those type of things. So just go into the control set 1, and over here in this particular I'm using Windows 9, so it is named as USB, just the USB folder. In maybe in some other versions it might be USB Tor or that you saw like in slide, the name that you saw in slide. So these are all the, like different instances of the USBs that I connected. So since this is a virtual machine, I haven't connected anything. These softwares, these folders are there by default, but if you connect a particular like USB, it will create an entry in this particular directory or in this particular registry key for that particular USB. And you click here, you can see just like, keep following it, and over there you can see the different details. So the hardware ID will be different, manufacturers will be different. So all of this information you can find for each of the different USBs that the user connected. Similarly, you can explore this Windows registry for at least the other things that I mentioned in the slides, like such as, the internet connections, the URLs, the recent files, those type of things, they can be found here in the Windows registry. So that can be, like an exercise for you. If you guys are interested, just look into these hives in your own machines and see if you find anything interesting. So that's all for the Windows forensics. And if you guys have any question about this whole topic, please email me or reach out to me using the Blackboard. You can message me over there as well. And this is like all the material that we have learned so far up till this point. It will come in the exam for your midterm. So everything is included, and this whole chapter of Windows registry, or sorry, Windows forensics until the prefetch files and the complete chapter and whatever we learned before that, all of that will be part of your syllabus for the midterm exam. So have fun, and please let me know if you have any question.